So we're going to go ahead and look at chemical equilibrium in this lecture set. So first we need to acquire an understanding of what it means to be at equilibrium or be under the equilibrium condition. Equilibrium is when the rate of two opposing processes are equal. So basically if we look at a chemical reaction like the one here, there is the process of going from reactants to products. And notice though that this arrow is indicating that we are also going from products to reactants. Okay, so there's two opposing processes that can actually occur. So initially though, typically we start with a certain amount of reactants, and so initially only the forward reaction is possible. But as the products begin to build up, the reverse reaction actually starts to occur and basically begins to speed up to counterbalance the forward process. So what happens is the reverse reaction speeds up while the forward reaction simultaneously slows down. Eventually though, the rates are going to become equal. So the rate of your forward reaction and the rate of your reverse reaction will equal one another. And at this point, you're going to have something called dynamic equilibrium. And that is the point where the forward and reverse reactions are happening simultaneously, but the concentration of your reactants and products maintain a constant value. So as we discuss, a reaction that's approaching equilibrium is going to have both its forward and reverse reactions occurring. So if we look at something like N2o4, breaking down to NO2, we end up with basically both products and reactants being present simultaneously and a progression towards having equal rates. So remember, initially there's only your reactant present. So since you only have your reactant present, the forward reaction is the only one occurring. Okay, as the amount of NO2 increases, the reverse reaction starts to occur and increases subsequently in rate. Okay, while this one is simultaneously going to be slowing down. So as that forward one slows down and the reverse reaction speeds up, you're going to basically reach a point in which the forward and reverse reactions are occurring at the same rate. Okay, so basically if we look at this diagram here, notice it relates rate versus time of basically your rate of disappearance of reactant and the rate of appearance of your products. Okay, and so basically you notice here that we have a slowdown of the rate of disappearance of our reactant, and we have an increase in the rate of appearance of our products. Okay, and eventually we get to a point where the rates are equal and equilibrium has been reached. Now, at this point, we need to look at what's actually happening with respect to the concentration of both reactants and products. So at equilibrium, the amount of reactants and products remains constant. Okay, so basically the exchange that's occurring back and forth is occurring in a way in which the total concentration of product and the total concentration of reactant remain constant. Now that's not to be confused with being the same or equal. So when I say that the amount of products and reactants remain constant, that means that those quantities that are produced are maintained. It does not mean that the concentration of product and reactant are equal. And we can see that here in this chart. As the reaction progresses and we reach that equilibrium point, remember our rates are occurring at the same rate. Our reactions are occurring at the same rate, both forward and reverse. But if we look at our concentration values, notice our concentration values are different, although that they remain constant in this progression. So we need to remember that the rate of the forward and reverse reactions at equilibrium are going to be proceeding at the same rate, and the concentration of your reactants and products are going to remain constant at equilibrium. So basically when you reach equilibrium, the amount of products and reactants that you have in the container should remain constant. However, that does not mean that the amounts of product and reactant are equal. So make sure that you are not confusing those two. So what would something like this look like in lab? Okay, well, in the macroscopic view, or the one that we can see with our naked eye, the reaction has actually stopped, or there's no reaction visible to us. We don't see any changes. On the microscopic level, the reaction is actually still occurring. Okay, what's physically happening is that that forward and reverse reaction are still occurring simultaneously at the same rate. The reason why we are not able to observe it with our naked eye is because, macroscopically, we don't see the exchange of atoms that are occurring. So let's go ahead and let's look at this concept with respect to a reaction that allows us to both visualize the progression of the forward reaction and basically what is maintained at equilibrium. So the decomposition of N2o4 into NO2 is something we've looked at before, but what we need to know about N2o4 is that it's a colorless gas and that the product, NO2, is a brown gas. Okay, so basically if we look at our progression of our reaction here, okay, notice in this case we have our N2o4, which is the colorless gas as discussed before. Okay, and as the reaction starts to progress towards products, notice that we are seeing a browning of that tube, and eventually we reach a fairly dark brown color that is maintained. Okay, so basically what we're seeing here from our macroscopic perspective is the progression of N2o4 breaking down into NO2 and then eventually reaching equilibrium. Okay, so this last picture here shows what this container will continue to look like theoretically for all time. And so what has happened here is that equilibrium has been set up or has been established. Okay, and so what's actually happening at this point is that the forward reaction, or the breakdown into the brown N2O gas, is equal to the rate of the reverse reaction. Okay, but the concentration of the two remain constant in that process. So that's why we won't see a change in the brownish color that we see here if we maintain the constant conditions. And that's because basically that amount of NO2 that's been produced is going to remain constant, and the concentration of N2O4 that remains is also going to remain constant. Now, that's not to say that the reactions have stopped happening. Remember, at equilibrium, you have a dynamic process that's occurring. You have both the forward and reverse reactions occurring simultaneously in order to maintain that constant concentration value. Okay, now, so if we go back and we look at this second picture here, notice that the coloring is a lot lighter than in the equilibrium state. And at that point, we know that equilibrium hasn't been reached because we can visually see that there's eventually going to be obviously more NO2 produced. Okay, so we haven't met that concentration value that's going to allow for equilibrium to be established. So at equilibrium, guys, the concentration of reactants and products is going to be constant. It's going to remain the same. Now, this is not to say that the concentration of reactants and concentration of products is equal. Okay, so at equilibrium, the concentration of the reactants remains the same, but that does not mean that the values of those concentrations are equal. So make sure that you get that into your head. Okay, now, neither reactants nor products are going to be leaving the system that has reached equilibrium, right? If we change the amount of our concentration, that's going to shift the direction in which the reaction will start to push. So the forward reaction would be encouraged, or the reverse reaction could potentially be encouraged depending on what we remove from the container. So in the equilibrium systems, you basically need to have a closed container. Okay, and as I said, the concentration values are going to be constant. Okay, so the ratio of those concentration terms are going to equal a constant. And we're going to talk about that constant in a little bit more detail here. So the equilibrium constant is a ratio between the concentration of our reactants and products. Now we can look at the equilibrium constant with respect to the rate laws of the forward and reverse reactions. Okay, so the forward reaction that we looked at a few slides ago shows the N2O4 breaking into the NO2. Okay, and the reverse reaction, the NO2 breaking, coming back together to form the N2O4, provides the subsequent rate laws we see down below here. So if these are our two rate laws for these two reactions, we know that at equilibrium, the rate of the forward reaction, okay, is going to equal the rate of the reverse reaction. So if we set these rates that we've established equal to one another, okay, and subsequently solve for the K values, we get this expression. So the K, or the rate constant of the forward reaction divided by the rate constant of the reverse reaction, is equal to the concentration of our product squared divided by our concentration of N2o4 squared. Okay, now this is what leads us to our equilibrium constant. So at a constant temperature, the ratio of our rate constants for our forward and reverse reactions is going to be equal to our equilibrium constant. So our equilibrium constant is related to our rate constants of our reaction, both the forward and the reverse, as well as related to the concentration associated with those rate constants. So we now have a relationship between the concentration of our products and reactants and our equilibrium constant. And we'll look at how to utilize this to do calculations and find out information about our specific reactions. So we can go ahead and write something called an equilibrium expression in a very generalized way, as we can see from the equation here that's provided here. We can write our equilibrium constant with respect to our products and our reactant concentrations and their subsequent stoichiometric relationships. Okay, so basically what we've done here is our equilibrium constant is going to be equal to the concentration of our two products to the coefficient in front of them divided by the concentration of our reactants to the coefficient in front of them. Okay, so basically this is how we write our equilibrium expression, and we can derive them from generalized chemical equations. Something that we'll go over in a little bit more detail in a few more slides basically indicates that pressure is proportional to concentration with respect to gases. So equilibrium expressions can also be written with respect to pressure or partial pressures. Okay, so just like we use the generalized equation here, if we're talking about the pressure of our reactants and products because they're gases, we can use the partial pressures of our products as well as the partial pressure of our reactants to the corresponding powers associated with their coefficient values. Okay, and we'll look at how to utilize that in a little bit. So we can go ahead and utilize the generalized equations up here in order to write equilibrium expressions for each of them. Okay, so if we start with this first reaction, okay, we're going to go ahead and write our Kc being equal to the concentration of our product, which is O2, to the third power because that's the coefficient in front of the O2, okay, and that's going to be divided by concentration of O3 to the second power. Okay, so that's our equilibrium expression for that specific equation. Okay, if we start with this next one here, okay, we're going to go ahead and write our equilibrium constant. Okay, once again, products to the power of the coefficient in front of that product to our reactants as such. Okay, and that's our equilibrium expression for the second one. And for the third one, it will look like the following. No power because there's a coefficient of 1. Okay. And then our reactants down at the bottom with the appropriate coefficients. So at this point, you guys probably understand or have noticed that when we're writing our equilibrium expressions, all we're actually looking at is the stoichiometry of the overall reaction. Okay, we don't actually take into account the mechanism because it's not dependent on the mechanism. The only thing that Kc actually depends on, or the only thing that your equilibrium constant actually is determined by, is the specific reaction that's being looked at and on the temperature. Okay. The other thing we need to understand is that the value of the equilibrium constant does not depend on the amount of reactants and products that you start with. Because remember, the equilibrium constant is based on values at equilibrium. Okay, so if we go ahead and we look at a set of experimental data, okay, notice we started with basically, in these first several, no N2o4 and a small amount of NO2. Okay, eventually equilibrium is reached. We measure the concentrations. Notice that our equilibrium constant is basically the same within the confines of experimental error. Okay, so basically we can start with no reactants and only products and reach equilibrium and obtain the same equilibrium constant. Okay, in that same way, we prove the other way. If we start with no products and allow the reaction to equilibrate, we eventually get the equilibrium condition as we see below, okay, and we subsequently get a equilibrium constant that is the same. So your equilibrium expression depends only on the stoichiometry, and it doesn't really matter how much of the initial amounts of reactants or products that you start with, as long as you have what you need to actually let the reaction occur. You subsequently will get a constant that is consistent within the confines of experimental error. Okay, so let's go ahead and let's do an example problem for the Haber-Bosch process, or the production of ammonia that we use to basically fertilize our forms and things of that sort. Okay, so at 27 degrees C, we have a concentration of 0.031 molar NH3, 0.85 molar N2, and 0.0031 molar H2. Okay, so these are the concentration values that we have for each of these individual components of this process. Okay, so we're going to assume that these are our equilibrium values. Okay, and before we move on and start plugging things in, we need to write our equilibrium expressions. So Kc is going to equal concentration of NH3 squared divided by N2 and H2 cubed. Okay, so if we go ahead and plug that in, okay, we end up with Kc equaling 0.031 squared divided by 0.85 and 0.0031 squared, cubed, excuse me. Okay, so we'll go ahead and plug that into our calculator, and we end up with 37,950 as our Kc value. So if we go ahead and we look at the next example problem, obviously we are now dealing with the reverse reaction. Okay, so these are our products. Okay, so they go up on top, and that's going to be divided by concentration of our reactant. Okay, we'll go ahead and we plug that in. 0.85, 0.0031 cubed divided by 0.031 squared. Okay, we plug that into our calculator, and that's going to give us 2.635 times 10 to the negative fifth as our Kc value for the reverse process. So let's go ahead and let's look at this last process. Notice we've divided through all our coefficients of our forward reaction by 2. Okay, so we're going to end up with NH3 divided by N2 to the 1/2 divided by H2 to the 3/2. Okay, we'll go ahead and plug our values in. 0.031 divided by our N2, which is going to be 0.85. Okay, put that to the 1/2, and then our H2, which is 0.0031, okay, to the 3/2. All right, plug that into our calculator, and we end up with 194.80, okay, as our Kc value. All right, now there are other approaches to how you could have done these calculations in a more simplistic way, and we'll look at those shortcuts in a little bit. Okay, but notice we've taken our concentrations at equilibrium and plug them into each of the individual equilibrium expressions, we get these equilibrium expressions from the balanced chemical equation for that specific reaction at that specific time. So I mentioned earlier that our equilibrium constant can be expressed with respect to pressure, okay, with a sub P below here. So what we've already been talking about is K sub C, and that C is referring to the concentration of your reactants and products with respect to molarity. When we have the subscript P, that's indicating a partial pressure value is being utilized. So something like ATM or torr, things of that sort. Okay. We still treat our equilibrium expression the exact same way as we treat Kc. The only difference is that instead of having concentration values here, okay, we actually use partial pressure values. So we'll have the partial pressure of our products divided by the partial pressure of our reactants to some power. Notice we're still using the coefficients as our exponential values in our equilibrium expression. Now, remember that our PC, PD, PA, PB are all the partial pressures of each of the specific gases in that container that correspond to that reaction at equilibrium. Okay, now, what you also need to understand, though, is that we can't just take Kp and Kc and interchange them. Okay, they're not directly interchangeable. The numerical values are going to end up being different. So we need to use care when we're, discussing things and making sure that we're indicating, are we discussing the equilibrium constant with respect to pressures, or are we reporting our equilibrium constant with respect to concentration values. Okay, now we're going to look at how to interchange between our Kc and our Kp so that a more direct conversation can be had. So what allows us to make the interconversion from Kc, okay, to Kp or vice versa is basically utilizing the ideal gas law. We do a bunch of rearranging with the ideal gas law, taking into consideration the Kp equilibrium expression, and we end up with this equation here, right? So your Kp is going to be equal to your Kc value times R, which is the gas constant from our ideal gas law, so liter atm mole Kelvin. Okay, are our units here. Our T is our temperature in Kelvin, and our delta N is the change in the gaseous products versus gaseous reactants. So basically, the number of gaseous products is going to get subtracted from the number of gaseous reactants. Okay, and so as I was mentioning earlier, Kp and Kc are different. Just something to note, K equilibrium, Kc, these are all things that you will see in text, and they all refer to the same thing. So they're referring to the equilibrium expression with respect to Kc. As I said, though, Kp is different, and so we need to utilize this equation in order to interconvert between our Kp and our Kc values. Okay, so we've been asked to calculate our K value. So when they just give you the generic K, we know that they're talking about our equilibrium constant with respect to concentration. Okay, so calculate Kc at 25 degrees C for the following reaction if Kp is this value. Okay, so we've been given our Kp, and we know that we need to interconvert between Kp and Kc. So Kp is going to be equal to Kc times RT change in N. Okay, so in this case, we know Kp, okay, we know R, we know T, okay, and we can figure out delta N. So in order to do this, we're going to find out all of our variables that we are going to plug in. So we'll go ahead and write all of those out first. Okay, R is that 0.0821 liter atm mole Kelvin. Okay, temperature is 25 degrees C, and we all know that if we add 273 to that, we're going to end up with 298 Kelvin. Okay, and then our delta N. Okay, remember our delta N is equal to the sum of our products minus our reactants. So we have 2 moles of NaCl, so 2 moles of our products minus 3 moles of our reactants. Okay, so delta N is -1. Okay, and we're going to subsequently plug this in to our equation that we have here. Okay, so if we want to isolate Kc, we're going to go ahead and do that first before we plug anything in. So Kp is going to be divided by RT to the delta N. Okay, and that's going to give us our Kc. Okay, so if we go ahead and plug everything in, 1.9 times 10 to the third divided by 0.0821 times our temperature, 298, okay, all to -1. Okay, plug that into our calculator, and that's going to subsequently give us this value. So the equilibrium constant in units should probably have kind of come up in your guys' head by now, and I hope you've noticed that your Kc and your Kp values haven't had any units. Okay, and so the reason why that's the case is because the equilibrium constants are actually derived from thermodynamic measurements, which we call activities, and they actually relate to ratios within a reaction set, and the units end up canceling. So basically, it's not out of the norm, or it's not abnormal for you to see equilibrium constants without any units. Basically, the way they're analyzed, the way they're being measured, causes this to be the case. And we'll look at the thermodynamic quantities a little bit later in the semester. Okay, but for right now, just understand that there is a reason why there aren't any units there. Okay, so let's continue our utilization of our equilibrium constant. Okay, so what's the point of K? What can K actually tell you about anything? Well, the values of K can actually dictate the direction or the quantity of products or reactants that you might have. So if you have a very large K value, what that means is that your reaction will basically lie to the right. So basically your products, okay, so if we're looking at a reaction of going from A to B, if my K value for this reaction is really, really large, it's much bigger than 1, okay, you're going to end up with a whole lot of products in terms of the substance that's going to dominate or be present in high quantity in that reaction flask. If your K value is much less than 1, your reactants instead, okay, are going to dominate, and the equilibrium then in that case is said to lie to the left. So basically you're going to have less product than you would anticipate having reactants. So when you hear, hey, the reaction lies to the right, that means that products are going to predominate, and if the reaction lies to the left, okay, that's going to be implying that your reactants predominate. So let's go ahead and look at this. So for a specific reaction, your equilibrium constant with respect to pressure at 298 Kelvin is 794, and your Kp value at 700 Kelvin is 22. So at these two different temperatures, okay, we have two different equilibrium constants. So Kp at 298 Kelvin is 794, and Kp at 700, so a higher temperature, is equal to 22. Okay, so we just said that if your K value is much bigger than 1, then your products dominate. Okay, and if it's your K value is smaller than 1, okay, reactants are going to dominate. So in this case, they're asking us, is the formation of products favored more at high or at low temperatures? Okay, so remember, the bigger my K value, the more products I'm going to have. So in this case, my K value is bigger at the lower temperature. So at 298 Kelvin, okay, I'm going to have more products. They're going to predominate in that situation. Okay, at the higher temperature, okay, the reactants are going to be present in higher quantity, and subsequently you're not going to produce as much product. So if we continue to look at how we can work with our equilibrium expression to solve for our equilibrium constant, we can actually kind of find some shortcuts to what we've discussed previously. So previously we had our balanced equations, we wrote our equilibrium expressions, and then we plugged in our concentrations at equilibrium and subsequently did the math to get our equilibrium constant value. And so that's how we would have obtained this equilibrium constant of this specific reaction here. Now we could then plug those same numbers into the equilibrium expression for the reverse reaction and get a new answer. But what I want you to notice is that for the reverse reaction, if you take the inverse of the forward reaction, you can subsequently get the reverse reaction. So if you have information about the forward reaction or about a specific portion of the reaction, you can subsequently skip the plug-in and multiply and divide approach and utilize this in order to get your reverse reaction. If I want to know what the equilibrium constant is for the reverse reaction, all I do is I take the equilibrium constant of the forward reaction, take the inverse of it, and subsequently get our equilibrium constant for a reverse reaction. Okay, so this can save you lots of time and effort if you just keep this in mind. So if we look at this problem, basically we take 2 moles of N2 and O2 to produce 2 moles of NO. And so for this reaction, when it's carried out at 25 degrees, we get this equilibrium constant. Now we can use this information to write the equilibrium constant expression and to subsequently calculate the equilibrium constant for this reaction. Okay, so what I want you to notice is that is actually the reverse of the reaction presented above. Okay, so let's go ahead and first write our equilibrium constant expression. Okay, so for this reaction here, Kc is going to be equal to our concentration of O2, concentration of N2 squared divided by NO squared. Okay, so that's our equilibrium expression. And then we can subsequently calculate for Kc of this reaction by taking the inverse of Kc for the forward reaction, which they gave to us right here. So K of the reverse reaction is going to equal 1 over 1 times 10 to the negative 30th. Okay, if we go ahead and plug that into your calculator, that's going to give you 1 times 10 to the 30th as your equilibrium constant for the reverse reaction. Okay, so hopefully you see how this shortcut can allow you to find out some information about a specific reaction without having to acquire a bunch of data points and subsequently manipulate the equilibrium expression. Notice we didn't use this at all in order to calculate Kc. We just used this relationship here in order to figure out what we needed to get. So we have a few more shortcuts to look at with respect to taking advantage of the relationships found with K and stoichiometry. Okay, so if we take this reaction here and we write our rate of equilibrium expression, we know that we could subsequently plug in some numbers and find what our equilibrium constant is for this specific reaction. Now, if we multiplied this same equation through by 2, we would definitely, of course, expect to get a different equilibrium expression with different values. We could subsequently plug in our numbers as well and subsequently find our equilibrium constant value for this new multiplied through reaction. Now, if I knew the original Kc of the reaction when it was unmultiplied, I could basically utilize a shortcut here in order to find out the new equilibrium constant. Okay, so in that case, what I would do is I would take the original K of the reaction seen here and raise it to whatever multiplier that I utilize. So if I multiplied through by 2, the n would be a 2. If I multiplied through by 3, okay, the n value would be a 3, etc. So basically, this is a nice little shortcut. If we know the original equilibrium constant, we can subsequently easily get the new one without having to plug any additional numbers in. Okay, if we divided a reaction through by some value, such as x, instead of raising our value, raising our original equilibrium constant to some value of n or x, instead we raise it to 1 divided by x. So if I were to divide through by 2, it'd be k original to the 1/2 power, or k original to the 1/3 if I divided through by 3. So these are two nice little shortcuts, and we will look at them and have practice with them as we continue to go through homework and such. And the last one I want to look at is if you sum up two reactions and you know their equilibrium constants, you can take the two equilibrium constants of the two reactions to get the new equilibrium constant for the new reaction that's produced. So basically, these are just nice little shortcuts along with taking the inverse in order to get the reverse reaction. And these will allow you to save lots of time on quizzes and tests. Okay, so just as a nice little summary, basically we write our equilibrium expressions with respect to balanced chemical equations. Our K value is going to be equal to the concentrations of our products to some power that corresponds to the coefficient in the balanced equation, divided by the concentration of our reactants to some power that correspond to the stoichiometry or the coefficient seen in the reactants of the balanced equation. So we know how to write our equilibrium expressions. We know that we're solving for our equilibrium constant. And basically, these are the equations that allow us to easily interchange between equations. So if I know the equilibrium constant for the forward reaction, in order to find the reverse, I just take the inverse of my forward value. If I multiply a reaction through by some number, I take the original unmultiplied equilibrium constant and raise it to whatever power I multiplied by. Okay, if I've divided through, I raise that original equilibrium constant to 1 divided by whatever I divided by. Okay, and if I add two reactions, basically I take the K values for each of the steps that are used to produce the overall new equation, and that will give me the equilibrium constant for the new equation. So as we also discussed, the thermodynamic aspect or the activities dictate that K has no units, but we have seen that K varies with temperature. Okay, so we definitely always need to check and see that our temperatures are consistent when we're comparing specific K values.